All right. So let's start with the following difficult question. If you're given two manifolds of the same dimension, determine if they are diffeomorphic or not. So is a manifold of dimension n diffeomorphic to another one? Of the same dimension. So we always kind of lean on very concrete examples of manifolds, so it might not seem that this is indeed a difficult question. But if you think about the way that manifolds are actually presented to one in the real world, then you can see that immediately that it's difficult. So in particular, let's say M was described to us as the inverse image of a point for some smooth mapping f from M to somewhere else, which we won't even name. Okay? And that N was described to us as a collection of sets where these are the domains of an atlas, or the domains of the charts of an atlas. So we know that these are two ways that manifolds can be given to us. So let's say M is given this way and N is given this way. How do you approach this question? What's your first step? It's not obvious, right? Last time we got our foot in the door, we stated the following fact, that if M and N are diffeomorphic, then their calculus or their calculus of K-forms are the same. By which I mean precisely the statement of this proposition which we proved last time. Okay? If they're diffeomorphic, then there is a diffeomorphism f from M to N. And for any form omega, if d omega is equal to 0, then d of its pullback is equal to 0. And this is if and only if. Okay? One direction is obvious. The other one we had to think about a little bit. Similarly, if omega is equal to d of something, then its pullback is also equal to d of something. Okay? So this is what we mean by the calculus of K-forms being the same. Okay? Derivative. So if your derivative is 0, it's 0 on both sides. And if you're the derivative of something, that's true on both sides. Okay? All right. So this suggests a strategy for attacking our hard problem. Maybe we want to develop a way to detect differences in the calculus of K-forms to prove that this would be a negative result, that M is not diffeomorphic to N. Okay, so maybe there's just some thing we can compute for M, no matter how it's presented, and thing we can compute for N, no matter how it's presented, and we can compare our two computations, and if they don't agree, maybe we know that they're not diffeomorphic. Okay? So we are going to carry out this strategy in a kind of classic example. So let's consider two manifolds of the same dimension. So M will be R2, and N will be R2 minus a point. So we'll take away the origin. Okay, and we are going to prove that these are not diffeomorphic. You might I mean, it's certainly not hard to believe, but it's not easy to prove. Okay, you have to introduce some new ideas. Just because this one's a subset of this one doesn't necessarily mean they're not diffeomorphic, right? So it's easy to produce examples where subsets of manifolds are diffeomorphic to the manifold. So R2 is diffeomorphic to the subset, which is the ball of, well, any radius actually, but ball of radius 1 around the origin. These two manifolds are diffeomorphic. Okay, so which sits inside of R2. So just because one is a subset of the other does not mean that they're not diffeomorphic. Okay, but we will prove that they are, and we will follow this strategy. So we want the calculus of K-forms to tell us the story. Okay. All right. So instead of just writing out the starting point, let's motivate it. We want a K-form to tell us that R2 is different than R2 minus the origin, okay, in some way. All right. So we're going to start with a K-form which sees the difference. All right. So how could a K-form, these are not the same sets. So we want a K-form which sees the difference of these two things as sets. Okay. So this one's missing 0. So the functions involved in the K-form do not have to worry about 0, right? So we could have the origin in our denominator, if you like, and not worry about it in this manifold, but we would have to worry about it in this manifold. Okay. So here is one form which sees this. So this is omega, and it will be minus x2 x1 squared plus x2 squared dx1. So already this is not a 1 form on R2, right? This is not defined at the origin. Okay? So this is not going to be the whole of our 1 form. We're going to have another term. It's also going to have a problem at the origin. And this is an element of, this is a 1, well, let me give myself some space. So this belongs to the 1 forms on R2 minus the origin. Okay? So this is a form which knows, well, which doesn't live here but lives here. So it knows the difference between these two, at least as sets. Okay? Now, of course, one could see the difference between these two sets in a similar way. So there must be more to the story, right? This is chosen to tell the difference between these two sets. There is no difference between these two manifolds as manifolds. Okay? So this must be telling a richer story. So let's get at it. We will establish the following claims about this form. Claim 1, as chosen, if you take the exterior derivative of omega, you will get 0. Okay, so this is given in global coordinates. We know how to do exterior derivatives, so I'll leave this as an exercise. But that's one reason why we chose that form. Okay? All right, claim 2. Omega is not d of anything. So for any smooth function or 0 form on R2 minus the origin, I'll just write like this to save some space. There's no function on the punctured plane is how we call that, whose exterior derivative is equal to omega. Okay? All right. And then to prove our result, we will prove a third. So we'll prove this and a third claim. That there is no such one form with these two properties on R2. Okay, so if eta is a one form on R2, and d of eta equals 0, then eta is d of something. Okay? So with these three claims and that proposition, we will be able to show that R2 and the punctured plane are not diffeomorphic. Okay, let's run through the endgame of the argument, and then we'll prove the claims. Okay. So let's follow this strategy in this particular case. So so we're going to argue by contradiction. Assume that they are diffeomorphic. Okay, we'll run into a contradiction. Okay, so we're going to run into a contradiction. All right, so claim 1 tells us that d omega equals 0. And so proposition 1 tells us that d of the pullback equals 0. Right? So proposition 1 tells us that d of f star omega equals 0. And now claim 3. So f star omega is a one form on R2. Right? We started with something here. We pulled it back to R2, and its d is 0. Right? So claim 3 tells us that it is d of something. So claim 3 would imply that f star omega equals d of some h. Okay. All right. But then proposition 1 tells us that means omega is d of something. Yes? So it's a one form in this case. So you just use our usual our 0 form. So I'll use our usual letters for functions. And this contradicts claim 2. Yes? It contradicts the claim that omega is not d of something. So to prove that R2, the plane and the punctured plane are not diffeomorphic, this argument tells us that it suffices to prove claims 1 through 3. Okay? Claim 1 is an exercise, which I will leave to you. It's just taking the exterior derivative of that particular form. So let's go on to claim 2. Okay? Does everyone understand the structure of the argument? All right, so let's prove claim 2. Okay, so we want to show that omega, this omega, is not d of something. So we're going to argue by contradiction. Okay? So assume that omega is equal to d of f. All right, where this is omega, of course. So we're going to derive a contradiction. Okay? All right, so how are we going to show that it's not d of something? Well, what do we know about one forms that are d of something? So Stokes' theorem tells us something about them. We know that if we integrate this over a manifold without boundary, then we will get 0. All right? So that's what we're going to do. So where is our manifold without boundary? Well, the only manifolds that we're talking about at this point are the plane, which has no boundary. But we don't know how to integrate over it because it's not compact. And this doesn't live on the plane. This lives on the punctured plane, which also has no boundary. Okay? So in fact, we're going to introduce a manifold without boundary into the picture. So consider S1. That's a nice manifold without boundary. And we can put it inside of either R2 or R2 minus the origin, right? And because we're working in R2 minus the origin, we want to put it. So we're going to include it in R2 minus the origin. And the map is as simple as possible. We take x1, x2, and we map it to x1, x2, right? You can draw the unit circle in R2 minus the origin, right? All right. So now, if we take J star, pull back of omega, omega lives here. We pull it back to S1. We get a 1 form on S1, right? So this is a 1 form on S1. We're assuming that, sorry, omega is d of something, right? And d and pullback commute. So J star of omega is equal to d of J star of f. And they all lie, they're all 1 forms on S1. Okay? So Stokes' theorem tells us that if we integrate J star omega over S1, that's equal to, as we just described, d of J star f, so d of something. And Stokes' theorem tells us that that is 0, right? Since the boundary of S1 is empty, right? All right, so where's our contradiction? Good question. Where's our contradiction? Well, we haven't gotten there yet. So what else can we do? We can actually just perform this integral. Right? This is something we can do. And if we don't get 0, then that's a contradiction. Yes? On the other hand, so let's do the computation. However, if we do this actual computation, well, let's do it. Okay, let's compute this integral. So we know we've done several integrals over the circle. We know that we're going to use our nice singular 1 cube, which just wraps around once and whose ends just touch, right? So this is equal to, as we know, the integral over gamma of j star omega, where gamma of t is our usual hero, cos 2 pi t sine 2 pi t. Okay? And so now everything's just a calculus problem. So this is, by definition, this is the integral from 0 to 1. And then we have to pull back this form to S1 by J. Right? So J is just inclusion. So what does this form look like? Well, let me gamma star of this thing. So what does J star of omega look like? Well, when we restrict it to the circle, these become 1s, right? So we have minus x2 dx1 plus x1 dx2. I just took this and I used the simplifying fact that we're on the unit circle to make these 1s. All right, now we have to do the pullback. So how do we pull back? We have the integral from 0 to 1. We evaluate this at our gamma 2, so that's minus sine 2 pi t. And then dx1, we take d of this, and right? So we get, so that's, yeah, and then we get another minus sign, so that's plus. And then we get sine squared, and then we get 2 pi dt. OK, you can check this. And then we pull back this part. We have cosine 2 pi t. And then d of x2, we get 2 pi cos 2 pi t. So we get cos squared, and then we get a 2 pi t, 2 pi dt. OK, and this integral is easy to compute. So, well, it's 2 pi. OK, which is not equal to 0. So this is our contradiction. OK, so here we didn't need the assumption that omega was exact. OK, we just computed. Here we use the assumption that omega is exact to derive the fact that this integral would have to be 0, but that's not what we got when we computed. OK? So we've contradicted this and shown that this is not true, so that omega is not d of something. OK? All right. Any questions? All right, so it remains for us, in order to prove that the plane is not diffeomorphic to the puncture plane, it remains for us to prove claim 3. OK? All right. Questions? So let's prove claim 3. So we have to show that if a 1 form on R2 is d of it is 0, then it's d of something. OK? So let's start with a 1 form on R2. So we have eta, a 1 form on R2. We know what it looks like, right? It's some function, let's say a of x1, x2, dx1 plus b of x1, x2, dx2. Right? And we want to assume that d eta equals 0. Right? So let's see what that looks like. Let's take d of eta. All right, so how do we do that? We take d of this function. It will have 2 terms. The partial derivative of a with respect to x1 dx1 plus the partial derivative of a with respect to x2 dx2. The first term, when we wedge product with dx1 will vanish. Right? So only 1 term will survive, and we get the partial derivative of a with respect to x2. evaluated at x1, x2, and then we'll have dx2 wedge dx1. And then when we continue to take the exterior derivative, we'll get the partial derivative of b with respect to x1 this time, evaluated at x1, x2, dx1 wedge dx2. All right, and this 2 form is minus that 2 form. So we see that the assumption that d eta equals 0 is equivalent to saying that dA by dx2 equals dB, the partial derivative of b with respect to dx1. Okay? All right, so this is what we're allowed to assume. Let's call that 1. Okay? And now we want to show that that implies that eta is d of something. Okay? So we have to find a function whose exterior derivative is this. So it's not so easy. You'll see that there's, the answer isn't maybe what you would guess. So let me tell you what the answer is, and then we'll prove that it's the answer. So we need to show that 1 implies that eta is d of h for some h which is a function on R2. So what is this function? Well, we know it's made out of a and b in some way, right? So how is it made out of a and b? So here's the claim. The following function works. So we're going to define a function. And it will be the following. Okay, so it's equal to x1 times the integral from 0 to 1 a tx1 tx2 dt plus x2 times the integral from 0 to 1 b of tx1 tx2 dt. Right, so if you integrate out the t's, this is a function of x1 and x2. So it's at least the right object. And it's not clear why it does the job. So let me give you the trick. Let's make an observation that involves functions like this. Yes?
Is there a reason the x's in the a and b are subscripts?
No, it's just sloppiness. Thank you. All right. So let's make the following observation. Observe. Okay, so let's consider a function of 2 variables, big F. Okay? And I want to express it in a way similar to this, involving integrals over t. Okay? So the first simple thing we can do is the following. So let's look at f tx1 tx2. Okay, so that's not equal to f, right? But if we evaluate it at 1, it is equal to f, at t equals 1. And if we evaluate it at 0, then it's not right. So let's put a t here. Okay? Now what do we see? If we evaluate this at 1, the t equals 1, we get f, the function. And if we evaluate it at 0, we get 0, the function, because of this t. Right? All right. So this sees f, but it's not f, so we have to. But we know that if we evaluate it at 1, it's OK, and if we evaluate it at 0, it doesn't matter. So what do? We take d by dt of this, and we integrate from 0 to 1 dt. Right? And now the fundamental theorem of calculus tells us that these sides are equal. Right? This integral is this evaluated at 1 minus this evaluated at 0. Yes? OK. So that was easy enough, but now we can rewrite what we have here. We can take this derivative inside the integrand and see what happens. Okay? So f is also equal to, and then there are 3 terms when we take this derivative. So we can think of this as the derivative of this function of t times this function of t. All right, so if we take the derivative of the first function of t, we get the derivative of f. I did it again. F of t x1 tx2 dt. So that's the first derivative here. And then I'm going to split out the other ones. So the next one, we have to leave this fixed and take the derivative of this thing with respect to t. That has 2 terms. This is a chain rule, right? So the first term is, well, the t stayed there, and we take the derivative with respect to t. In the first argument, we have the partial derivative of f with respect to its first argument, which is named x1. And then we take the derivative of this function of t, and we get a factor of x1. And we evaluate this at tx1, tx2, dt. Yes? And then there's another term. We have tx2, and then the partial derivative of f with respect to its second variable. And then we evaluate it at its argument. OK? So in short, this observation can be summarized as this. If we see this expression involving the function big F, that's just big F in disguise. OK? All right. So let's see why that is relevant. We want to show that d of h equals omega, or eta, sorry. So now we're going to show that d of h equals eta. So d of h by itself is the partial derivative of h with respect to x1 dx1 plus the partial derivative of h with respect to x2 dh2. Right? That's the exterior derivative of any function on R2. And we need to show then that dh dx1 equals a, and dh dx2 equals b. Right? Then this will be eta. Yes? All right, here's eta. OK? All right. Good. All right, so I'm going to show one of these, and you're going to do the other one. This is the same. OK? So let's take the partial derivative of little h with respect to x2. OK? So where's our h? Our h is here. All right, so let's work here. Well, OK, let's remember this. OK, we have this to work with. Let's put it over here. So recall that we have the partial derivative of a with respect to x2 is equal to the partial derivative of big B with respect to x1. All right. So now let's compute the partial derivative of h with respect to its second variable. All right. Good, so here's our formula for little h. So when we take the partial derivative with respect to x2, the partial derivative comes inside the integrand, and we take the partial derivative of this, right? So this term will give us one term. So it's equal to, we have x1 on the outside. We have the integral from 0 to 1. And when we take the partial derivative of the integrand with respect to x2, we get the partial derivative of a with respect to its second argument. And then it's evaluated at tx1, tx2. And we're taking the partial derivative with respect to x2. So a t comes out. Yes? And then we integrate, so dt. Good. And so we're taking the partial derivative of this whole thing with respect to x2. So now we do this part, right? And we get two terms. We get, we take the partial derivative with respect to that thing. So we get plus the integral from 0 to 1 bt of x1, tx2 dt. So we took the derivative of this x2. And now we have the derivative of this one, which we do in the same way as before. So we have x2 on the outside now, the integral from 0 to 1, the partial derivative of b with respect to its second variable, evaluated at tx1, tx2 dt, and then we get an extra factor of t here in the derivative. OK. All right, but now we can use this fact, right? We want this to equal b. And so the obstruction here is a, which has nothing to do with b in general, but it does have this to do with b, right? So we know that by 1, we can replace this with b dx1. So here we've used this equality 1. OK? And now, well, this is a bunch of integrals involving b and its partial derivatives, right? But if we compare it to our observation, it's exactly what appears here, right? For this function f. We see the integral of b, right? We see this thing, that's the second term. And these x1, this x1 can come inside the integral, right? This is an integral with respect to dt. So x1, we can think of it as lying inside or outside the integral. Doesn't matter. So if we put it inside, it's identical to these types of expressions. Okay, so this equals b of x1, x2 by the observation. Okay, and so with that, we're done. We have shown that these are equal in exactly the same way using this equality again. You can show that these are equal, and so the dh is equal to, we've just shown it's equal to eta. Okay? Okay.
So who came up with this derivation?
So this is a simple version of what's called Poincaré's lemma. I'm not sure it was Poincaré, but I'm not sure it wasn't. I don't know. You know, sometimes things are named after people who made them famous rather than people who did them. But there's a good reason Poincaré is so famous, so there's no reason to doubt him. OK. Yes. So here we've kind of secretly exploited the fact that our manifold is convex. So when we take t from 0 to 1, all these points, tx1, tx2, lie inside our domain. So this makes sense. You probably didn't question it, right? But if you ask whether this generalizes to other domains, they would have to have this property. And when you include that kind of condition in the statement, then it becomes what's classically known as the Poincare lemma, which holds for convex sets. OK? Just in case you've seen it elsewhere, you might have remembered convexity and not seen it here. OK. Now I just wanted, any questions about this? So now we've proven that R2 and the punctured plane are not diffeomorphic. All right? But the ideas that we've used generalize dramatically. So I'm going to give you the names of these tools. Okay? It's good to know them. So the ideas from the example we just did generalize quite dramatically. So let me describe this generalization to you. The ideas are no more difficult. There's more to talk about. So let's let M be an n-dimensional manifold, and let's let it be compact for simplicity. OK? Doesn't have to be, but it's easier to talk about it quickly if we assume it's compact. OK? And then let's fix some integer for, between 0 and a dimension. OK? So we'll call that k. And now we're going to define the following. So we're going to define zk to be the set of k forms on M such that d of them is equal to 0. OK? So this is like the omega in our example. OK? So these are referred to as closed k forms. OK? We won't use that language past today, or I might not. Anyway, these are closed k forms. Now let's consider another set, bk. These are omegas. So k forms on M such that omega is d of something. So these are called exact k forms. OK? All right, so the omega we wrote down before would lie in this set. But if our manifold was the punctured plane, it would not lie in this set. Right? Because it wasn't d of something. We proved that. OK? So just some simple observations. Zk and bk are vector spaces. Right? If you add two things whose d are 0, then d of their sum is 0. And if you multiply them by a scalar, the same is true. And anyway, it's easy to see. It's easy to test that they are vector spaces just by the formal definition of what a vector space is. And bk lies inside of zk. And in fact, it is a subspace. Okay? So if our manifold was R2, bk would equal zk. Everything which is everything where d is 0 is d of something. We proved that. That was claim 3. Okay? All right. And why is this true? Well, so if you're d of something, then if we take d of both sides, you get d alpha, which is 0. Right? So this is clear? All right. So now here's, we're going to take this subspace of a vector space, and we're going to do the following. So we're going to define H superscript k to be, so let me just, the quotient vector space zk over bk Okay, so let me tell you how to think of this. Okay, if you haven't seen quotient vector spaces before. So this is zk modulo an equivalence relationship, which we've talked about. We've talked about equivalence relationships before, where when are two things equivalent? Where, let's say, omega is equivalent to beta. So omega and beta are closed forms, and they're equivalent. That just means that if we subtract them, then that difference is in BK. Okay, it's D of something. Does that make sense? So you can just think of identifying all the things in BK inside of ZK. Okay? That's one way to think of this. Okay? So if ZK was R2 and BK was the x-axis, it's just like you're left with the y-axis. Okay? If you want to think of it geometrically. Okay? All right. Good. And so here's the nice result about these objects. So these are just formal versions of things we've considered in the previous example. Let's say it's a proposition. Let's make it a theorem so I can differentiate the two. So it's a theorem. HK is a finite dimensional vector space. Okay, so ZK and BK are definitely not finite dimensional. They're like spaces of functions, if you like, locally, right? They're infinite dimensional. But this quotient defined like this is finite dimensional. All right? And so one thing we can associate to a finite dimensional vector space is a number, its dimension. Right? So set B sub k of m equal to the dimension of this vector space. So this is a number. Right? It's a national, well, okay, it doesn't matter. All right. So now look at what we've done. We start with a manifold, and we've created a list of numbers. Very simple set of objects. A manifold could be very complicated. F inverse of Q, where F is some map to 12 copies of RP2. It doesn't matter, right? It's a manifold. But to this manifold, we've associated now something very simple, a list of numbers. Okay? And this list of numbers has the following remarkable property. If M and N are diffeomorphic, then the kth number for M equals the kth number for N for all k equals 0 to N. Okay? So now these are tests. This is a whole list of tests we can apply to manifolds to detect if they're not diffeomorphic. Right? If you compute two of these numbers for the same k, but for the two manifolds, and they're not the same, that means they're not diffeomorphic. Okay? So we applied this test in our example. If you can rewrite it in that language. Okay. And in fact, this is not as far removed from what we've done. This follows exactly from proposition 1 that we stated at the beginning of today's lecture. Okay? So this is, let's call this proposition 1 star. It's just written in a different language. Okay? You can show that, so I'll leave that as an exercise for you in logic, actually. You've done the hard work. You just show that the previous version of proposition 1 implies this. Okay? So just in case you're wondering, these B's are called the Betti numbers of the manifold. If you've heard that phrase before, now you've learned what they are. Okay? And they're tests as to whether or not it's diffeomorphic. They're not perfect tests. It's not true that if these equalities all hold, then M and N are diffeomorphic.